In this video, we'll take a look at section 10.2 in correlation. So the types of data that we'll look at in chapter 10 is bivariate data, and that means how two sets of data are related to each other. And if you think about scatter plots that you've done in other classes or finding line of best fit, that's what this relates to. So section 10.2 is something called correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other. A linear correlation exists when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. The way that we measure the strength of this correlation for linear is something called the linear correlation coefficient R. And the value, there's formulas in the textbook. We're going to go ahead and have the calculator take care of it for us. The correlation R is also sometimes called the Pearson product moment correlation coefficient after the Carl Pearson, who was a statistician who originally developed it. So what is R? We'll be using the calculator to calculate it. The value is between -1 and 1 always. So what does that mean? What we'd like to be able to do is interpret. So if a set of data has a positive linear correlation, if you take a look at this set of data, the scatter plot isn't exactly in a straight line, but it looks like it could be linear and then it is increasing with a positive slope. So this is called a positive correlation, and notice the R is 0.851. So that's closer to 1 than it is to 0. The next one has a slightly tighter grouped bunch of scatter points on the scatter plot, and notice from left to right it has a negative slope. So that correlation is negative. So positive correlation goes with positive slope, negative goes with negative slope. That's a negative 0.965. That's very close to -1. So that would mean that those 2 points, two sets of data, are linearly related. What zero correlation looks like is when the scatter plot is just all over the place. There's no apparent linear pattern at all. And then a nonlinear relationship, such as a quadratic or something else, will have a correlation pretty close to 0. So how do we make that distinction? Well, let's take a look. In our example, we have a table showing annual data for various years. Okay, the data are weights in metric tons of lemons imported from Mexico and car crash fatality rates per 100,000 people in the population in the United States. So two things that you wouldn't normally think would go together. Is there sufficient evidence to conclude that there is a linear correlation between weights of lemon imports from Mexico and United States car fatality rates? Then we want to take a look, do the results suggest that imported lemons somehow cause car fatalities? So if we take a look at our data, again, these are from selected years. So in this particular year, we imported 230 metric tons of lemons from Mexico, and in that particular year, there were 15.9 car crash fatalities per 100,000 people. So how do we check and see if these two data are linearly associated or a correlation? So we take a calculator and we're going to type our lemon imports in list 1 and fatality rates in list 2. So we get 230, 265, 358, 480, and 530. Those are our the lemon data. L2 we have 15.9, 15.7, 15.4, 15.3, and 14.9. Okay, there are sets of data. I'm going to go ahead and hit second quit. And I have an additional step here. Let's take a look at a scatter plot just so you can see how the data values are related and see what they look like. If you hit second y equals, we're going to choose stat plots, turn them on, and what we want to look at is the first type of plot right here, which is the scatter plot. The x list is L1, y list is L2, and choose whatever mark that you want on there. And then to graph statistics graphs, you hit zoom. Oh, you know what I forgot to do? Let me go back here. I don't have anything in the y equals, so just a reminder to check your y equals and make sure you don't have anything in there that it's going to graph over the top. So we're going to hit zoom. Option number 9 is zoom stat, so it will automatically set the window for us. So weirdly enough, if you look at this scatter plot where x is weights of lemons and y is fatality rates, they look to be pretty close to a straight line with a negative association, so that our R value will end up being negative. All right, step 3, there's a couple of ways to find just the R. We're going to use stat tests, a linear regression t-test, because we're going to use this again in section 10.3. All right, so we hit stat, over to tests, scroll down until you get linear regression t-test, hit enter. We have our x's in list 1, y's in list 2, frequency. We'll learn what these mean in the next section. Select not equal to 0. Regression equation, we'll use this in the next section as well. We don't need it here. And then calculate. The only two items we need from this test are the p-value, which is a 0.0099, and also the R value. If you scroll down, there's a lot of other information in here. The correlation coefficient R is a negative 0.9589. So to answer the question up here, is there evidence to conclude that there's a linear correlation between weights of lemon imports and car fatality rates? The answer is yes. Our R value is close to -1, and this p-value right here is always the significance level. If that's lower than 0.05, if we're not given a significance level, it means that, yes, that these two values are linearly associated. So yes, there is a linear correlation between those two, and the strength of that is measured by R. So a very important, and reason why I picked this example, do the results suggest that imported lemons cause car fatalities? And the answer is absolutely not. So just because two data values are correlated, there's a linear correlation between them, it doesn't mean that one causes the other to happen. It just means that there's a linear association of some sort.